Today we'll be starting a new chapter. Okay, see, this chapter is called or is named as electrostatic potential and capacitance. So today we're starting this new topic. I hope you don't have any problem in the previous topic. If you at all have something, you can ask me anytime. Okay. Okay. So now, so see, first of all, we have to learn. See, in the previous class, we have a previous chapter, we have learned electric charge, then electric fields. So now we'll be learning electrostatic potential and capacitance. These are also related to somewhat charges. And see, there we had learned that if you keep a charge around it, it creates an electrostatic field. And what that electrostatic field does, this that electrostatic field actually exert a force, right? I'll just show you here. So we have seen in the previous chapter that if I have a charge q, then just 1 minute, I'll just close the window. There are a lot of sounds. Yeah, I'm back. So we have seen in the previous chapter, if we have a positive charge, so it will create an electric field around it, and we have seen that electric field will be radially outward like this. We have seen that. So electric field was denoted by E. And how do we actually examine whether there is electric field or not? We have to bring a test charge. So test charge we had brought and seen that this test charge small q is experiencing a force. This is experiencing a force. So this force actually we have seen eventually that was q into E. So this is what we have seen in the previous chapter. Now look, uh, if we have certain electric field, okay, created by some charge distribution, and if I bring a charge, test charge, okay, suppose there is a test charge of a source charge q, I am bringing a test charge inside its field somewhere at distance, some smaller distance, okay, some distance smaller. I am bringing this test charge over here. So look, my electric field, see, there is a repulsive force right between these two because of this electric field is exerting a force on the charge. So we'll be having, we know even from the Coulomb's law, we have this q by 4 pi epsilon naught r square. This is a repulsive force. So what we have to do, if I actually want to bring a test charge from somewhere to a point inside an electric field, okay, inside an electric field, what I have to do, actually I have to work against the electric field we have in this direction, or the repulsive force we have to work against. So if we have to work against the electric field or repulsive force, then I have to have one external force which is actually able to overcome the electric field, okay, which is able to overcome the electric field, right? So that you can bring some charge from somewhere to a certain distance, like certain point inside the electric field created by this source charge capital Q. So what we have to do, we have to do certain work done against the electric field, okay. So that electric field has to be that work done has to be done by an external force. That means we have to apply some external force to bring the test charge. Okay, that external force is doing some work. So that is into the D. So this is external force into D. Okay. So we are talking about potential. So before we will be learning potential. Before we learn potential, we have to learn the potential energy. We have to learn what is potential energy. So if you remember in your 11th standard, there is a chapter called work power energy. So where you have learned the concept of potential energy. You know the potential energy cannot be arbitrarily obtained for any kind of force. So potential energy is actually relevant only for conservative force field. Conservative force. Conservative force. So here electrostatic field is conservative force field, right? Conservative force field. That's why we talk about potential energy. So what is potential energy actually? When you have to work, okay, you have to do work against some force, okay. Suppose you are in this case you are bringing a charge from some distance to some place to some other place. Suppose this is the place which is at r distance from any arbitrary charge capital Q, which is situated at the origin, suppose arbitrary origin. So if you are bringing that, you have to do certain work against the electrostatic field or the Coulombic repulsion over here. So see, electrostatic field is conservative force field. So whatever work you do, that work will be stored as potential energy. If suppose at this point you have brought the charge, so in this charge at this point the charge small q will be having, sorry, not small q, at this point the capital Q will be having the potential energy, which is actually the work done by the external force to bring that test charge here. If this is r distance, this is F into r. Okay, what is the force? Look, force will be your, yeah, force is the electric force, the electric field into Q. So again you will see this will be r square proportional to E, will be proportional to r square, and K, it will be here K, and there will be another K Q here, K Q by r square into r. So you will see, so okay, this expression is not very important now. Okay, what is important is that the potential energy is relevant for the conservative force field, because in that case the work done we do, that is against the force we have to do, and that work done, whatever work done we are doing, that will be stored as potential energy at particular point, at any point. Suppose I bring the charge over here, so at this point the potential energy will be different, and if we bring at this point the potential energy will be different. So in each point, so the work done is different, amount of work done is different, so the potential energy also will be different. And in this case the work done, see, in case of conservative force field, the work done does not depend on path. Does not depend on path. Which way you bring to that particular point, it does not depend. It depends only on the final points. Okay, final positions, initial and final position. Then and it depends so this is one of the characteristics of conservative force field, that the work done by the force does not depend on the path. And for a cyclic path, if the initial and final positions are same, the work done will be 0 for cyclic path. Okay, I'll tell you what it is. Suppose there is a path like this, to start from A, go to B, and come back to again B. Okay, go to B this way and come back this way to again A. So you are going A to B, then coming back B to A. So what is the work done in this case? Work done is 0 because your initial and final points are the same, A. So it depends, work done depends on only on the initial and final configuration of the charge particle. Okay, or the position of the charge particle. So these are 2 points. If I remember some other points also, I'll tell you. And now look, in your book, what we are doing is actually, see, we are bringing a charge, test charge, from some point R to P. So this P is actually at R distance from the source charge Q, which is situated at arbitrary origin in this case. And here suppose both the charges are positive charges. So there will be repulsive force. You have to do some work if you want to bring the charge, and that work who is doing, that is actually done by the external force. And so since it is done by the external force against the electric field, so uh, this external force will be exactly equal to the electric field but opposite in direction, and the work you do to bring the charge, bring the test charge Q to P, that work done will be stored at this point P as the potential energy. Okay, potential energy. So this is what has been written over here. You look, the work done by the external force in moving a charge from Q to Q, a charge Q from R to P is this R to P integration external force into dr. So external force is actually exactly equal to the electric force or the Coulombic force or the force exerted by the electric field. So that has been written over here, minus E, and opposite I said. So that is the work done. So this work done against the electrostatic repulsive force, and gets stored, not N should not be there, gets stored as a potential energy. At every point in the electric field, a particle with charge Q possesses a certain electrostatic potential energy. So do you understand why? At any point of any electric field, so wherever there is an electric field, if you just go point to point, one point to another point, every point you will have certain potential energy. Okay, certain potential energy. That means, okay, so the Q is here, capital Q. So I am bringing at P from where R, positive small q charge. So when I am bringing, if I bring at P point, there will be certain potential, and there will be certain potential at R also, right? Because I have to bring this charge from somewhere to R. So there also will be certain work done to be done. So see, suppose the potential energy at, so there will be everywhere, every point there will be certain potential energy, because this, see, this charge has created an electric field in which you are bringing the charge. So because of that, you have to do certain work. If you are bringing from some point to R, so you have to do certain work. So that work will be stored as potential energy at R point. And when you are bringing the charge from R to P, you have to do again some work against the electric field, external electrostatic field. So for that case also, you have to do some work. That work has been stored as potential energy at this particular point. So what is the work done? Can you tell me? For bringing R to P, what is the work done? I can write, see, UP minus potential energy at P minus potential energy at A is the work done we have done, external work done, say, suppose A, R to P minus AP dot dr. Okay, AP dot dr. So this is actually a work done. Work done is nothing but the difference in the potential energy. See, the work done we have to actually do, or the external force has to do, is nothing but the difference between the potential energy between these 2 points, UP minus UR. Do you agree with me or not? Because I have to do certain work to bring up to here. I have to do certain work from to bring the test charge Q from here to here. So what is the potential energy? Priyadarshini, just I'm getting a call. Just a minute. Hello. 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 Who is this? I'm sorry. So yeah. Excuse me. Yeah. So you look here. So work done is, so what I can write is work done is nothing but the difference in the potential energy UP minus UR. So generally potential energy is, or energy density is denoted by U. Okay, in mechanics. Okay, or in electrostatics, anywhere you go, potential energy generally denoted by U. So potential energy at P is UP, potential energy at R position is UR. So this difference is nothing but the work done, what external force has to do to bring the test charge from R to P. So that is what they have written in your book. You look here. So they have written this one. So work done. So the potential energy difference is nothing but the work done. Okay. So RP. Okay. So this is the point here. Now here the point I have already made. Already I have told you that the so the potential energy at individual point is not of that importance. Okay. The physical quantity which is important is the work done or the potential energy difference. Okay, potential energy difference or the work done is relevant physical entity, but potential energy at each and individual point does not make much sense. If I give you certain example in case of uh, from gravitational potential energy, you will be able to appreciate this concept that potential is not that of important quantity, but the difference in the potential. Suppose, see, in case of gravitational potential, see, suppose I just lift one object of mass m up to certain height h, okay, against gravity. Gravity is down. So suppose this is the height h. So what is the potential energy? What is the work done I have to do? So work done means what? M into G. This is the this is your force here, m into G, and how much I'm going? M into G into H. So what is the potential energy for this particular position then at H? So mgh. Okay, mgh is the potential energy. But this is not very important. Important is what is the potential energy difference between these two positions. That is the work done. If the potential energy here is 0, potential energy here, suppose this point is P, suppose UP is 0, then I can write the work done as suppose this is R point, so UP minus U, sorry, UR here, UR minus UP. So what does it mean? See, mgh minus 0. So which is actually mgh. So this is actually important quantity. So potential energy is a relevant quantity than the potential energy at every point. So potential energy difference is the relevant quantity. So which we can equate to work done. Okay. So potential energy difference is a relevant quantity. So look here, this potential energy concept, as I said, can be actually, see, in this case, see, the potential energy depends only on the final points P and R. So we can see this kind the potential energy when depends only on the end points. That means in which force field we are in conservative force field, and potential energy, concept of potential energy is relevant or meaningful only for this kind of force field, conservative force field. If the potential energy depends only on depends on the path also, then potential energy will not be that much appreciable, or the concept of potential energy would not be meaningful if the work depend on the path. Okay, because we can yeah, so that is the thing. So path dependence, independence of work done by any by an electrostatic field can be proved using Coulomb's law, but which is actually out of our syllabus now, so we are not doing. So you can understand. So what is this point saying? Actually, this point is saying that the potential energy concept is relevant only for conservative force field, and for that case only the potential energy depends on the final and initial position, does not depend on the path. If it depends on the path, then it is not that meaningful. Another point, as I said, the potential energy is actually not very relevant. At each point the potential energy will be different point, there will be different potential energy. But what is meaningful is the potential energy difference, which we can equate to work done, that I have shown you. So in other words, what it is saying is, actually, see here it is written, what this means is that the actual value of the potential is not physically significant. It is the potential difference, potential energy difference, which is significant. Okay, so for that case what I can do, see, if that is the case, is the if the potential energy difference is the relevant quantity, then what I can do is, at each point I can actually add certain positive constant or negative constant. Okay, whatever constant you add to each point as potential energy, with the potential energy you have to add for both the points. Suppose, okay, I am trying to make you understand what does this mean. So potential, since, so see, I have P point here, this is R point, this is my P point. Okay, I told this UP is here, UR is here. This is what I told. And look here, the work done is actually relevant, which is actually potential difference, potential energy difference, potential energy difference. Potential at individual point is not that important. Okay, because we cannot relate to work done over there. Okay, for individual point we cannot relate to that. So that's why when you go from one point to another point, we are doing certain work, and the potential energy difference is actually relevant for us. So actually, it, you see, in other words, I can say, if I tell that this the potential energy is P, instead of saying U suffix P, I can just add a constant potential, okay, alpha. Similarly, I can add another constant, like same constant with UR. So does it make any difference? Does it make any difference if I take the difference between them? Ultimately, what I get, work done is equal to UP minus UR, because this same alpha will be like cancelling the alpha from the other potential, right? So this again meaning that I can add or subtract subtract any any uh, constant term okay, constant term with, okay, with the potential energy at every point. Okay, when I take the difference, ultimately what I get is the difference in the potential. So that will be equal to the work done between in bringing from one point to another point. Okay, so see here, up plus alpha minus ur minus alpha. So this two goes off, right? So you will get ultimately this one. Again, this actually infer us that we can choose what this infer actually. This infers that we can choose the reference for potential energy calculation. You might be thinking, sir, what you are teaching us today, we are not able to understand. Okay, I'll just make you understand. So just a minute. Oh, shit. Okay. So what does that mean? What? So in any case, whether it is mechanics, whether it is electrostatics, wherever we talk about potential energy, we have to always set a reference point. Reference point. Reference point or level. Reference level to measure the potential energy. I'll tell you what it is. Okay. So generally, reference level is set at a position or a level where the potential energy is zero. So where we set our reference level for the potential energy is zero. I'll give the same example. In case of gravitational potential energy, we had set the ground or the earth surface having potential energy zero. Do you remember that? This is H. I have taken M, object of M mass. So mgh was the potential energy for this point. And with respect to what? With respect to the ground. When you calculate the potential energy with respect to ground, this guy at this height, okay, the mass at this height has potential energy mgh. So see here we have set a reference level, so that is on the earth. So in case of gravitational potential or whatever, so we have to set always a reference level to calculate or to measure the potential energy. So in this case, look, our work done is up minus ur, right? That means when we bring a test charge from some r point to some point p, then whatever work done we are doing, that is called the potential energy. Now what we have to define a reference level where the potential, so reference level means, as I told, reference level means in general we set the potential, initial potential energy at zero level. As I told you, for gravitational potential, ground level is zero potential level. So when this potential will be zero, actually at infinity we'll show you that. When we calculate, we'll show you how at infinity the potential energy will be zero. Electrostatic potential energy or gravitational potential energy also you can see at infinity. Okay, at infinity the gravitational potential energy, sorry, electrostatic potential will be zero. That means this r we have to shift to where? Infinity. At infinity we have to shift. So if we bring a charge positive charge Q or unit positive charge, we will see that a positive charge Q from infinity to this point P, the work we have to do, that is actually called the potential energy at this particular point P. See, then it will be P infinity. So this will be infinity. Instead of R, we will be write infinity. So at infinity, what is the potential energy we have set? Since it is a reference level, so that is 0. So UP minus 0. So ultimately, what you get is the potential energy is P. So you can understand that see, this is the definition of potential energy. So what is the definition? Work done, okay, by an external force against electric field, okay, so work done by an external field against the electric field. So while bringing a, this is my version of definition, you can see from the book proper. So this I am writing such that you can understand. While bringing a positive charge, okay, positive charge from infinity to a certain point. So obviously the potential energy at any point, we have to write potential energy at any point. Energy at any point is equal to the work done by an external force against the electric field while bringing a positive charge from infinity to that point, okay, to that point. So this is the definition of the potential energy, okay. We'll see in the book. So this part in the beginning, it in every chapter you look like little bit boring, and sometimes it will be little difficult to understand, but as you listen to me properly and read the book, you will come to know, okay, eventually you will understand. If you don't understand, you can tell me again. See, this is the definition they have told you. See, the potential energy of a charge Q, okay, at any point, okay, is the work done by the external force, in bringing the charge Q from infinity to that point, okay. So this is the definition you have to write. If you have to write in your exam, you have to write this definition, okay. This is the definition, okay. So this is your potential energy. Now we'll learn electrostatic potential. So as I told you that potential and potential energy, they are little different. Little bit of difference is there. We'll just learn what is that difference, okay. What is that difference? We'll learn now. Just a minute. So we have learned potential energy. Now we'll be learning potential. What is potential? Okay. And this is electrostatic potential. So what is the potential? We have learned the potential energy, that is electrostatic potential energy. So this is electrostatic potential. And see, electrostatic potential is related to electrostatic potential energy only. So what we have learned? We have learned that work done is actually nothing but difference in the potential energy that we have learned. If I write explicitly P infinity, so UP minus U infinity, that is what we have learned. So this is actually, and we have defined that if you bring a positive charge to a certain point, so potential at that point will be the work done stored in that. Okay, so what is that work done? Work done against the electric field. Okay, so here the potential actually denoted by V, potential denoted by V. In fact, as we know, the potential energy difference is more relevant than potential energy at individual point. Similarly, potential difference, suppose A and B, 2 points are there, A and B. So this is A, this is B. So potential, it has suppose B potential, here B A potential. So the more relevant term for us will be potential difference, that is VA minus VB. Okay, and potential. So electrostatic potential is nothing but what, that is actually the work done per unit charge distribution. Okay, we'll learn that. So potential or potential difference is denoted by V. Okay, so potential difference is denoted by V. Okay, and we have seen the potential energy was denoted by U. So potential difference is actually denoted by the work done by work done per unit charge. Work done per unit charge. See, actually, what we have seen, see whatever work done and what all those things we are talking, this is actually due to the electric field, right? Due to the electric field, right? Work done we have to do against the electric field. That means if there is no electric field, there will be no work done. We don't have to do any work against this, against any force. So see, we have to define a term which is directly, see, work done is actually proportional to charge Q, right? Because I know that the force, external force I have to apply is proportional to Q only. And I know work done is equal to F into R or F dot dr. If my force is more, then my work done will be more. So, and force is depending on what? Force is depending on the charge, test charge I bring. Why? Because the force, external force is exactly equal and opposite to the electrostatic force. What is that? E into Q or Q into E. So this is the test charge here. So if you bring more charge, you get more work done. If you bring less charge, you get less work done. So see, this actually, this depends on, this work done depends on the test charge. So work done depends on the test charge you bring. Okay, so it is directly, so work done is not directly related to electric field, it even related to the charge also, test charge. So you want to define a quantity which will be irrelevant or which will not depend on. So you see, if I divide the work done by Q, if I divide the work done by Q, then this quantity which I have denoted here has V, which is nothing but potential at each point, or potential difference also I can say. If I write P, Q, PR, so this will be also PR. So this is the potential difference. Okay, so this is the quantity which is actually relevant for us. Why? This is actually, this has a direct relationship with the electric field. What does it mean? If I know the potential, I know exactly what is the nature of the electric field, because there is no influence of the test charge I bring. I don't know whether you are understanding. I'll just repeat this concept. Why I am defining one after another. I am defining a new quantity. Once I define potential energy, okay, then I am defining potential. You might be thinking, sir, what is this? Is it so much relevant for us to understand? Yes. Why? See, whatever I am seeing, whether it is potential energy or whether it is potential, it has they are directly related to electric field. But which quantity? But which quantity is more relevant or can give more direct picture or clear picture of electric field, whether potential energy or potential? Because see, it is potential because potential energy actually related to the charge. So potential energy is nothing but the work done, and that is actually directly related to what? The test charge I bring. That means, and see, this F is equal to Q into E. So this is how it is related actually. That means if I know the work done, I don't know exactly, like I don't know directly what is the picture of this, or what is the situation, what is the configuration of the electric field, or the electric field itself we cannot understand, because there is an influence of the test charge also. So I have to define a quantity where there will be no influence of this test charge. That means what? If I just define the potential energy difference, uh, if I divide the potential energy difference with Q, that means work done per unit charge. This is actually a relevant quantity which is directly giving the picture of the electric field. Okay, or directly it talk about or gives the nature of the electric field. So this is called electrostatic potential, which is defined as, so V, electrostatic potential defined as work done per unit test charge. Work done per unit test charge. So do you understand why we have defined, rather than potential energy, we have defined potential, electrostatic potential? Why? Because this gives the nature of or the configuration of the electric field directly, because here there is no influence of test charge. Okay, so this is one important concept. What is, yeah, that is why a potential or potential difference is more important than the potential energy here. See, here it is written, okay, external force in bringing a unit positive charge. Okay, this is the potential. Okay, this is the potential. So you read it. If you don't understand the sentences here written, I'll tell you again. So this is the definition of the work done by an external force in bringing a unit positive charge from infinity to a point is equal to the actually electrostatic potential. This is the perfect definition for you to write in exam. Okay, so this is now if I have, if I if I bring many charges, now if I bring many charges from certain point to, like in many paths, see, suppose I bring q1, q2, q3, all the charges in different points. So at p points, what will be the potential? So that we can find out, that we'll be doing here in the next section. See how we can find out. So this is, yeah, so look here, we have to now calculate potential due to a point charge. So how to do that? Consider a potential q, a charge q, point charge q, which is actually situated at origin at O here. Now the same example I have taken, okay, what I have taken in the beginning. Okay, same thing here. So that for definiteness, let us take q to be positive, and we used to determine the potential at any point p, which is at r distance, okay, away from the q. I have to actually I have to calculate potential due to this capital Q charge at p, okay, which is at r distance away. How to do that? I have to bring one test charge, unit positive charge, 1 coulomb. Suppose here 1 coulomb charge has been taken from where? Infinity to this point p. Then the work done for that unit charge to bring at p will be actually the potential for this point p, potential at this point p for this capital Q charge. So how to do that? Look here. First, what we are doing, we are actually bringing the test charge 1 coulomb charge, unit charge I am saying. So 1 coulomb charge, according to the definition, I am taking 1 coulomb charge or unit charge from infinity to p prime. First I have brought, then I will bring from p prime to p in a small steps. Okay, suppose first I bring an arbitrary small distance delta r prime, then I bring another delta f prime, like that I am bringing closer and closer and closer, and at finally I'll be bringing over here at p. So see, now we have to calculate the work done, right? Work done for this. So to calculate the work done, what we have to do, we have to actually find out the force first and the displacement, then we have to multiply. So what is the force? So we have to see how much force field, how much field is created by this capital Q charge at particular this point p prime, suppose in the beginning. So that will be, so this is the r prime distance from Q to p prime. The distance is r prime. So what is the field created by this? So Q by 4 pi epsilon naught r prime square. So what is the force experienced by this 1 coulomb charge? So that is Q into E. So Q into 1 by 4 pi epsilon naught r square, and this is the direction along this way. Okay, towards the infinity. So my r is actually r is decreasing while force is actually away from the point O. That's why this work done has been given as negative sign here, because the delta r has a negative sign. As I bring near, the difference between the point P and P prime is decreasing. That's why this delta r will be negative. So they have put here negative. So first I am just doing, like, I am calculating the work done for bringing a elementary small distance, that is delta r prime. Then I'll integrate that for the whole distance. Okay, whole distance r. So that is what has been done over here. You look here, this is the elementary work done. Now I have to integrate it. Okay, if we integrate it, see this delta r, if you take, see if you take the delta r tending to infinity, tending to 0, then you can write this as actually integration from the calculus. You can write as, in place of delta r you can write dr. So that is what has been done here. And now the limit I have to take for r prime is from infinity to r. Okay, infinity to r. If you do this integration, you look, this will be 1 by r. Okay, minus 1 by r. So that minus will goes off with this. Okay, so if you just put the limit, you look here, q by 4 pi epsilon naught r, and lower limit is 1 by infinity. 1 by infinity is nothing but 0. So what I get, the potential expression for potential for a point charge is this one. See, q by 4 pi epsilon naught r. See, look, I'll just tell you one thing, one important thing. So earlier we have calculated the electric field for a point charge. So that we have got as q by 4 pi epsilon naught r square. Okay, this we have got. Now what is the potential you got? Now you got potential at any point r from the charge q, at any point r. Okay, suppose r, this is the point p. So 4 pi epsilon naught r. So how is potential varying and how is electric field varying? So electric field is varying as 1 by r square. Okay, and the potential for a point charge is varying as 1 by r. If you draw, okay, electric field and potential together with distance, so how do they look like? Suppose electric field and potential both you draw. So look, the potential will actually die out little slower, like this, slower than this is potential 1 by v is proportional to 1 by r, but the electric field will die out very soon. It will decrease like steeply because it is 1 by r square. Okay, it is 1 by r square, so it will decrease very steeply like this. Okay, like this. So E is proportional to 1 by r square. Okay, so this is what is drawn in your book. You look here. I hope you have understood how we have derived this potential for a point charge. Okay, actually in fact you don't have to actually, in your exam you may not get a question derive an expression for a expression for potential at any point r due to a point charge. You may not get this kind of question, but we will be using this result. Okay, we will be using this result to derive many other derivations. Okay, many other derivations. So if you know, like whenever we require to write potential for any point charge at certain distance, so what you have to write, that is the value of the charge divided by 4 pi epsilon naught r. R is the distance where you are calculating the potential. Now look, we'll be, see here it is shown here. See, look, the potential is actually dying slowly than the electric field. See, electric field is dying very faster. So it is drawn here. You can look. Now we'll just actually derive an expression using this value, using this result, that for a point charge, what is the potential? The potential for a point charge at any point r is actually q by 4 pi epsilon naught r. So that using that value or that concept, we will be actually deriving potential for a dipole. Okay, we'll derive potential for a dipole. Look, sorry, I'll just copy this figure. Okay, we'll derive potential for dipole. I'll just remove this. So what is our aim now? What we are going to do? We are going to derive an expression for potential for an electric dipole. Okay, for an electric dipole. So look, here I have taken the electric dipole. What happened to him? What happened to Nikhil?
Don't know, sir.
Okay, does, I don't know whether he has class. Do you know whether he has class after that?
Don't know, sir.
Okay, then, yeah, because you people have joined late, and we had, like, I had to start a little late. So shall we stop it here for today, because he is not here? Otherwise,
Yes,
I
sir.
have to again repeat the same thing. Okay, then I'll stop it here. Okay, next day we'll start from here. Okay.
Yes, sir. Thank you, sir.
Okay, then bye.